Hello, physicists, and welcome. In this session, we'll be looking at rotational work, energy, and power. Let's get started. Hey, just a note, go through a couple of symbols, equations, and then 4 example problems. All right. Hey, so let's take a look at our variables, symbols, and units. Work, we'll use the symbol W. Of course, it's measured in joules. Our work and energy is precious, so we measure it in joules. It also has the unit Newton meter, but that translates to a joule, and it's our energy transferred. Hey, energy, we'll use a capital E for total energy, and that's broken into a couple of different types. Potential energy will have the U and then a subscript indicating what type of potential energy. For kinetic energy, we'll use the symbol K and a subscript on the type of kinetic energy. And then power, we'll use the symbol P, measured in watts. Probably one of the units that we're more familiar with is a joule per second. It's the rate that we do work or the rate at which energy is transferred. Let's take a look at our equations or relationships in both the linear, the translational, and the rotational worlds. Hey, as we know, our work is equal to the integral of force dx. If our force stays constant across a range, then that just simplifies as force times distance. Again, in the rotational world, our work is tau d theta. Tau is our torque. Theta is our angular rotation or angular position. And if our torque stays constant with rotational position, this simplifies to tau theta. Hey, our kinetic energy in the translational world is 1/2 mass times velocity squared. The analogy in the rotational world, our kinetic energy for an object that's rotating is 1/2 I. Remember, that's our moment of inertia, or also referred to as our rotational mass, times omega squared, omega being our angular velocity. Hey, for a spring, I'm using the U for our potential, the sub ST, the sub S for a spring, and T for translational, is the integral of the force that the spring is exerting with its extension dx. Most often in an ideal spring, that's just kx times dx. So in an ideal case, that integral just becomes 1/2 kx squared. The analogy in the rotational world, again, I'm using the U sub S to indicate that's a potential from a spring, again, a conservative force, but in this case, rotational is the integral of k theta d theta. Now, that's assuming that that tau for our spring, okay, is a function of how much it's wrapped up. Okay, if that remains constant, then it simplifies to 1/2 k theta squared. Hey, power is the rate at which we do work. So our average power is work over the amount of time it took to do that work. We could also look at our power as the derivative of energy with respect to time. Again, in the rotational world, that looks very much the same. Our average power is the work we do divided by the amount of time it takes. Or we could say, hey, it's the derivative of energy with respect to time. Another way we could look at that, hey, we know that power is our work divided by time. Hey, if I break this out, I can see that it's force times distance divided by time. If I separate out distance divided by time, that's velocity. So another way we can express our power is our force times velocity. Hey, and the analogy in the rotational world is that our power is theta omega, or torque times our angular velocity. Let's go through a couple of example problems. Hey, I have a flywheel is a large disc, or disc, depending on how you want to spell it and where you are, that's used to moderate sudden changes in angular velocity. A particular flywheel has a mass of 3 kilograms and a radius of 0.4 meters, starts from rest, and an electric motor with a torque of 50 Newton meters is used to start the flywheel spinning. Friction in the supporting bearings causes 6 Newton meters of frictional torque. After 10 complete rotations, 1, calculate the work done by the motor. 2, calculate the rotational kinetic energy of the flywheel. Hey, so in number 1, we want to find the work done by the motor. Hey, so we are given that the torque of the motor is 50 Newton meters. And remember, that's not the same as joules, because our newtons and our meters are at right angles. So that's Newton meters, a measure of torque. And our theta is 10 revolutions. If we want to convert that to radians, we'll have to multiply that by 2 pi. Remember, 2 pi in every full rotation. Hey, our relationship is this, that work is equal to the integral is our torque d theta. What's nice in here is that our torque is staying the same all the way through. So we could just say our work is torque times theta. Let's go ahead and solve this now. Okay, so I solve. I see that work is going to be equal to our torque, 50 Newton meters. Our angle is going to be, or our change in position, 10 revolutions times 2 pi. What does that work out to be? 50 times 10 times 2, I get 1,000 pi Newton meters. Notice now, hey, this Newton meters is now our energy. So it's 3,141 roughly Newton meters, also called 3,141 joules. Hey, now number 2. Let's take a look at what are we trying to find here? We're trying to find our rotational kinetic energy. Hey, let's see what I'm given. Hey, I'm given the torque of the motor, 50 Newton meters. Our torque due to friction is 6 Newton meters, and that's from these bearings. There's a shaft that supports the flywheel. We have a bearing here. We'll assume that that's in the opposite direction of our torque. And distance is 10 revolutions times 2 pi radians per revolution. Look at our relationship. Yeah, a relationship that, what's our big idea here? Net work creates kinetic energy, right? So with that, let's see if we can come up with some ideas. Hey, so my work net is going to be equal to my torque net times my distance, or change in angular position. See, our torque and our torque is staying constant all the way through that. Let's put some numbers in here. Let's go ahead and solve this. Our net torque, 50 minus 6, is going to give us 44 Newton meters. So we'll end up with our net work, which becomes our kinetic energy, rotational, is going to be 44 Newton meters times 10 revolutions times 2 pi, 880 pi. So that works out to 2,763 Newton meters, also called joules. Okay, so let's take a look at the next problem. All right, we have a ball, 0.2 kilograms, diameter 6 centimeters, is at rest at the top of a hill. It rolls down the hill. The hill has a height of 3 meters without slipping. And calculate 1, the translational speed at the bottom of the hill, and 2, the rotational kinetic energy at the bottom of the hill. Then we got 3. Some ski resorts open during the summer for downhill mountain biking runs. Assume no non-conservative forces and no pedaling. Which method would go top to bottom more quickly? All right, hey, let's go ahead and draw a picture here. Hey, so I've drawn a picture here. We have our ball, which we can consider a solid sphere, starting at the top of this hill, ends up down at the bottom of the hill. Hey, we have a kind of an odd path here, but because we're looking at, we'll treat this as an energy problem and a gravitational potential energy. All we're worried about is the height of our beginning and ending points. We don't have to worry about the odd path we're going along here. And so this one, we're trying to find the velocity translational. We're not looking at rotational velocity at the bottom of the hill. What am I given? Hey, I'm given that the height of the hill is 3 meters. The mass of the ball is 0.2 kilograms, and I'll assume it's a solid ball. Okay, I'll put solid ball, so it's a solid sphere. The diameter of the ball is 6 centimeters. Anything else we have on that? And rolls without slipping. That's going to be important for this calculation, as we saw with the refried beans and what was it? The chicken broth rolling down the incline in class. Okay. Hey, let's take a look at our relationships. We have several here. Hey, I'm trying to find the velocity at the bottom of the hill. And what other things do I know? Hey, I've got some type of gravitational potential energy at the top of the hill that if I roll down is going to become kinetic energy. So that's one idea. Hey, another relationship is my total kinetic energy is going to be made up of my translational kinetic energy plus my rotational kinetic energy. Well, that's going to be important because I know that my kinetic energy is 1/2 mv squared, and I'm looking for that. Okay, that's good. Hey, I also have my rotational kinetic energy is 1/2 I omega squared. Hey, if I'm looking through here, hey, omega, I know there's a relationship between velocity, radius, and omega. That's going to be an important relationship here. And it looks like I'm also going to need the relationship for moment of inertia. Hey, and for a solid sphere, this would be one of the values you'd like to memorize. I find that it's 2/5 mr squared. All right. Hey, so let's do some simplifying before we solve this here. Hey, so it looks like, let's see, my gravitational potential energy becomes my kinetic energy, which becomes my translational and my rotational. So I'll say it's equal to 1/2 mv squared plus, let's start doing some substituting in our other equation. 1/2 looks like my moment of inertia. I could say that is mr squared. And then how about this term over here? I have v equals r omega. I could change that around, dividing each side by r, and I find that omega is equal to v over r squared. Hey, something handy is going to come into effect here. Oh, I got to change one thing here. Let me just update this. I have to update moment of inertia here. So sorry about that. I didn't convert that properly yet. Okay, sorry about that. I've replaced that value for I with 2/5 mr squared. Let's go and simplify this a bit now. You can find out that a lot of our work is actually done in establishing our relationships here. All right, hey, so I see that looks like I have my r squared here, and this r squared will cancel. Those 2's cancel, so I have 1/2 mv squared plus 1/5 mv squared is going to be the energy at the bottom of the hill. Let's go ahead and solve that. 1/2 mv squared plus 1/5 mv squared, I get common denominator 7/10 mv squared is equal to our gravitational potential energy, mgh. You notice something, that mass cancels here also. So changing this around, I get v squared is equal to 10gh over 7. A couple things that are interesting here. Mass has disappeared, so regardless of the mass of the ball up here, it won't change the velocity. Also, radius disappears, so as long as it is a solid sphere, regardless of the mass or the size of the ball up here, it will end up having the same velocity at the bottom. Let's go and substitute some numbers in here. V squared is equal to, let's take the square root of each side. 10, height 3 over 7. Let's take the square root of that. Okay, 10 times 10, 100 times 3, 300 divided by 7. That's what, 42.8 meters squared over seconds squared. We'll take the square root of that. About 6, a little more than 6, a little less than 7, 6.54, so meters per second. That's our velocity at the bottom of that hill. Okay, the translational velocity. Number 2, Okay, what do we take a look at this one? Hey, number 2, the rotational kinetic energy at the bottom of the hill. Hey, we'll take advantage of this. We did some substituting down the lower corner, and we found that our rotational kinetic energy, yes, it is equal to 1/2 I omega squared. It's also equal to 1/5 mass times velocity squared when we did all the substitution based off the geometry. 1/2 our mass, 0.2 kilograms. Our velocity, 6.54 meters per second. We'll square that value. I plugged it in. Let's say 6.54 squared. We'll get back to our 42.8 times 0.2 times 1/2. I get a value of about 1.71 joules for our rotational kinetic energy. And the last question here. Some ski resorts open during the summer for downhill mountain bike runs assume no non-conservative forces and no pedaling. Which method, that would be skiing or mountain biking, would you use to go from top to bottom more quickly? Taking a look at distribution of energy. If I'm skiing, nothing is rotating, so all of my gravitational potential energy up here goes into translational kinetic energy here. If I'm in a bike, you can see that we have wheels that are going round and round. So some of that gravitational potential energy also goes into rotational kinetic energy. So there's less translational kinetic energy. So I would have a slower velocity with the bike at the bottom. The skiing would get me from top to bottom more quickly. Okay, let's get started on this next problem. So a torsional spring energy storage system for bicycle wheels is being evaluated. The hub-mounted nonlinear spring applies a torque of, and it gives this formula, a torque of K1 theta plus K2 theta squared, where K1 is equal to 12 Newton meters per radian, K2 is 1.5 Newton meters per radian squared. Remember, K can be is a spring constant, whether it's for a linear spring or for a torsional spring. And the torsional spring is cranked 2 times and attached to a wheel. Mass of the wheel, 0.5 kilograms, diameter 700 millimeters. Assume all mass at the full radius. Okay, determine 1, the energy stored in the spring, and 2, the angular velocity of the wheel when the spring is completely unwound. Start with a picture. I'm going to try drawing bicycle wheel. They tend to be fairly thin, like the one in the classroom. They have spokes to minimize their mass, like that. And it says that our torsional energy storage system is hub mounted. And so mounted on here, and it just has kind of a couple of wraps, and then maybe it has some type of a pin like that. So when we crank it, it keeps wrapping up. All right, so first one, what are you trying to find? We're trying to find the energy stored in the spring. Well, energy stored looks like these systems are conservative forces. So if we want to find the energy stored is from our work. Okay, so we could just really say, hey, what's the work on the spring? Given a couple of things. So we have torque is equal to K1 theta plus K2 theta squared. Theta is going to be equal to 2 turns, so we'll have to multiply that by 2 pi to get our radians. Looks like, I think that's going to be all we're going to need. All right, hey, our relationship is that work is equal to the integral of torque d theta, and this one, our torque is changing with theta because we have a fairly complicated relationship, and that is, let's see, 12, I'm going to leave the units off for right now. It makes it a little bit easier probably to see. Okay, 12 Newton meters per radian theta plus 1.5 theta squared d theta. Let's do the integral of, okay, let's go ahead and solve. Let's take the integral of that. So when you have that work, take the integral, add 1 to the power, I get, what is it? 6 theta squared plus 0.5 theta to the third, and we'll evaluate that from 0 to, let's see, our new theta is 2 times 2 pi, 4 pi. Let's go ahead and put those numbers in. So we have 6 times 4 pi squared plus 0.5 4 pi cubed. Put that in the calculator. Let's see what I get. This value is 990. 4 pi squared times 6, I get 946. I add those up. And what do I get? I get 1936. Notice these are Newton meters, but now because it is actually work, we can call it 1936 joules. So that's the work we did on the wheel, or on the spring. That becomes the energy stored in the spring. 2, the angular velocity. So what are we trying to find? We're trying to find omega final, given. Hey, so we're given that our potential energy in the spring is what, 1936 joules. We also know that at the end, okay, that final, I guess I call it final, is equal to 0, and it all goes into kinetic energy. Okay, what's our relationship? That we know that when we're looking for angular velocity, we know that K rotation is equal to 1/2 I omega squared. That's what we're looking for, is omega. For a bicycle wheel with all the mass on the outside, we know that the moment of inertia is mr squared. Okay, let's go ahead and solve this now. Okay, so we're solving for this. We know that, so we have 1936 joules is going to be equal to 1/2 mr squared times r omega squared. So I'm going to bring this up over here, do a little more work. Okay, what is it? 1936. I'm going to drop the units just for right now, is equal to 1/2 our mass is 0.5, 0.5. Our radius, notice that's 700 millimeters for a diameter, so our radius is I'm getting close to the edge, 0.35 squared, and that's all times omega squared. Okay, so I know that, let's see, I got 1936 is equal to, what do we got here? 1/2 times 0.06125 omega squared tells us that omega squared is going to be equal to 63,216. Take the square root of each of those. Our omega is equal to, what do I got? 251 radians per second. What does that work out to be? Hey, that's about, divided by 2 pi, that's about 40 rotations a second. Hey, we got a gasoline engine is used to run a pump that lifts 1,200 liters of water per minute from a reservoir to a storage tower with a height of 30 meters. Assume no pumping losses, and the water exits the discharge nozzle at 4 meters per second. So 1, calculate the power required to pump the water. 2, the engine torque if the engine runs best at 1,800 RPMs. Let's get started on this one. I got a water tower. Okay. And it looks like I got some type of a motor and a pump that is sucking up water from some type of a reservoir up to a pipe that exits into this storage tank, and it's 30 meters above water level. And the water comes flowing out of here at 4 meters per second. Okay, so the first thing, what are we trying to do? We're trying to find power. And what are we given? Hey, so we are given that we have 1,200 liters per minute, have H, 30 meters, velocity at the exit, was it 4 meters per second? Anything else in here? Hey, we're on Earth, so we'll assume that gravity is equal to 10 meters per second squared. Okay, relationships. I'm looking for power. I know that power is equal to my change in energy over my change in time. And our energy in this case, increase in gravitational potential energy plus change in the kinetic energy. And this is going to be translational. We'll assume there's no vortex or weird spinning going on in there. Other relationship, we know that gravitational potential energy, mgh, kinetic energy, translational, is equal to 1/2 mv squared. Go ahead and solve this thing. I'm going to do a little more symbol manipulation first. So I know that power is equal to change in energy over my change of time. So let's go ahead and change this a bit. So we're going to say it's going to be mgh over t plus 1/2 mv squared over t as well. Hey, what's nice is, let's take a look at this. We have m over t here and m over t here. Do we have a rate? Yeah, so we've got this. We've given 1,200 liters per minute. One other relationship is that we have a mass. 1 liter of water has a mass of just about 1 kilogram. All right, so at 1,200 liters per minute, I'm going to divide that, so I find that my mass per second is going to be 1,200 kilograms per minute divided by 60 seconds per minute. Mass per unit time, 1,200 divided by 60. What does that work out to be? That's 20 kilograms per second times 10 times the height of this, 30 meters, plus, hey, and look at our kinetic energy. We're going to have 1/2 mass per unit time. We're having, that's 20 kilograms per second, and our exit velocity is 4 meters per second squared. Let's do a little bit of math here, and we'll find out what we have. Yeah, I have 20 times 10, that's 200 times 30. If I did that right, I got 6,000 joules per second, plus 4 squared, 16 times 10, that's another, not a whole lot, 160 joules per second. Joule per second is the same as a watt. So our power, 6,160 watts. Okay. Probably tell that's about 6.1 kilowatts, about 8 horsepower or so. So number 2, I'll squeeze it in over here. Sorry about that. And the last thing we want to do, we want to find, let's see, power required to pump the water. Okay, engine torque. Okay, you often probably have heard engines, they end up giving 2 specifications, a horsepower or power rating and a torque rating. Well, we've already found out what the, are given. I'll separate this. Are given is that the power is 6,160 watts. Okay. And also we have our angular velocity, right? 1,800 RPM. We'll have to convert that a bit. All right. We have a relationship between power is equal to our torque times our angular velocity. Angular velocity is going to be equal to our RPM times 2 pi divided by 60 to get this into radians per second. Let's go ahead and solve this now. So 1,800 times 2 pi divided by 60, and I get that value is about 188. So I'm getting this a little bit crowded. So our final solution is our power is 160 watts divided by 188 radians per second. Gives me a value of, 32.7 Newton meters. Remember, this is a torque, so it is Newton meters, not joules. A unit you may be more familiar with would be foot-pounds. This is probably about 25 foot-pounds of torque. Okay, I think that's it. So for now, that's physics.